Hello viewers, Wagadaruna taking you through the story for A-Level Physics Paper 2, and this video I'm going to go through this marking guide for Test 4, which was on reflection of light at plane surfaces. So just start with question 1. Question 1 part A says, show that for a ray of light passing through layers of transparent media separated by parallel boundaries, n sin I is equal to A, where A is a constant, n is the refractive index of the medium containing angle I. So we shall consider a ray of monochromatic light traveling across parallel-sided media 1, 2, and 3 as shown. So we need a diagram to ease on our derivation. So that will be medium 1, medium 2, and medium 3. So this is also medium 1. So we have a ray incident from medium 1 and is with an incident at an angle I1, so it is refracted with an angle of refraction R2. So then here now it will be the angle of incidence I2 in medium 2. It is also refracted with an angle of refraction R3, which is in the medium 3. Then this I3 is the angle of incidence in medium 3, so it will be refracted to R1, which is the angle of refraction in medium 1. So note that when it's medium 1 we use subscript 1, medium 2 we use subscript 2, medium 3 we use subscript 3, medium 1 we use subscript 1. So that is very vital, because in the question they told us that I is the angle in that medium. So that we shall come and say that for a ray moving from medium 1 to medium 2, the refractive index is given by n1 to 2 and is given by the expression that n1 to 2 is equal to sine I1 over sine R2. So what is here is what is here, what is here is what is here. So from this to this is the angle of incidence and this is the angle of refraction. So the order of these matters. So that is the marks for this slide. But we also know that n1 to 2 is equal to n2 over n1, and also R2 is equal to I2, alternating angles. Therefore, you shall come and substitute where there was n1, n2, shall put their n2 over n1, and where there was R2, shall put their sine, we shall put their I2. Then from there we shall cross multiply to come up with this and call it equation 1. That was for a ray moving from medium 1 to medium 2. What about for the ray moving from medium 2 to medium 3? So the refractive index is given by n2 to 3. And has the form expression that n2 to 3 is equal to sine I2 over sine R3. Like I told you, these subscripts are very vital. What is here is also what is here. Then you also know that n of 2 to 3 is the same as n3 over n2, and R3 is equal to I3, alternating angles. Therefore, we shall come and substitute. Where there was this, we shall put there this, and where there was R3, we shall put there I3. And cross multiply to come up with equation 2. So from equations 1 and 2, we shall come up with that expression that all these are equal. What does that imply? It implies that n sine I is a constant, because this one for medium 1, this is for medium 2, and this is for medium 3, and they are all equal, meaning that this n sine I is equal to a constant. And basically that is what they wanted. So now we shall go to part B, Roman 1. So B Roman 1 says that what is meant by critical angle. So you come and say that the critical angle is the angle of incidence in the denser medium for which the angle of refraction in the adjoining less dense medium is 90 degrees. So the ray must be propagating from denser medium to less dense medium. The order matters. So that was part B Roman 1. Now we shall go to part B Roman 2. Roman 2 says, describe an experiment to determine the critical angle for a water-air boundary. So we need to draw a diagram to ease on our description. So that's the diagram. We have to label it. This is the monochromatic source of light, and this is the air cell, this is the circular scale, and this is the observer, and this is the ray of light, ray of monochromatic light. And that is the water, and this is the transparent glass vessel, and that is how the marks will be awarded for this slide. So now that you have drawn the diagram, let's go and see the description. So you start by saying that two glass slides are cemented together in form of an air cell. The air cell is dipped into water in a transparent vessel having thin plane parallel sides. I think you saw that in the diagram. So this is the air cell, and this is the transparent vessel, and this is the water. So the air cell is placed into the water enclosed in the transparent glass vessel. A narrow beam of monochromatic light is directed normal to the air cell and is viewed by the observer from the opposite side. So this monochromatic light is viewed by this observer on the other side. So the monochromatic light was on one side, the observer is on the other side. The air cell is then turned in one direction, not this word, in one direction, until light is suddenly cut off from the observer. This position is noted on the circular scale. So in this case, this ray, the observer is able to view this ray of monochromatic light because it is incident at 90 degrees. So when it is incident at 90 degrees, there will be no refraction. Therefore, that is why it passes through and this observer is able to see it. But when you rotate this air cell, the angle of refraction will keep on changing. At a certain point, it will be cut off completely because it will glaze the surface of the air cell. and when it is cut off, that position will be noted on the circular scale. So the circular scale is used helps you to measure the angle. Then the air cell is turned in the opposite direction. So this word, one direction and opposite direction, have to be seen until light just, know this word, just. So just, you can either use the word just or suddenly. Both these two are the same. So just disappears again. The position is noted on the circular scale. So I've got two positions of extinctions, and the angle between the two positions of extinction of light is measured. So this angle theta is measured between the two positions. When you get that, it implies that the critical angle will be equal to half that angle between the two. So it will be equal to theta over 2. So C is the critical angle, and it will be given by theta over 2. And basically that is what they wanted in this part. So that is how marks would be awarded. So now we shall go to part C. So part C says the figure below, so this is the figure, shows an isosceles prism ABC of refractive index 1.51 dipped in a liquid with its refracting edge downwards. A ray of light incident on the prism at an angle I equal to 34.6, so this is the angle I which is equal to 34.6, emerges perpendicularly through the base. So this is what they mean by perpendicular. Calculate the refractive index of the liquid. So let's first redraw the diagram to help us ease the calculation. So with this as the angle of incidence, the angle of refraction will be this R1, and here it will be R2. Now here there is refraction, total internal refraction, therefore this angle will be equal to this angle. That is why you also see here R2. Okay, so what about this one? If you look at this, the whole of this is 90 degrees. So what does that mean? If this is 90 degrees, this remaining part will be 90 minus R2. So 90 minus R2. When this is 90 minus R2, and this is also 90, it implies that this remaining angle can be got from angles of a triangle. So when I add this 90 plus R2 plus 90 plus this angle here, let us call it alpha, then you equate it to 180 degrees. You realize that alpha will be equal to R2 because this and this will cancel with this. Therefore, alpha will be equal to R2. That is why I have put here R2. Then also you realize that here there is R2. The reason is because they told us that the triangle is isosceles, implying that these two sides will be equal, implying that this angle will be equal to that angle. So now we shall come and do our calculations from triangle ABC. So this is what I was telling you, how to get R2. Now to get R2, shall use the whole of this triangle A, B, and C. Angles of the triangle, they add up to 180. Therefore R2 will be equal to 50 degrees. But we know that this one plus this is equal to this. I think you remember that under introduction to prisms. So when I add these two, I'll come up with, they will be equal to this angle. Therefore I can easily get my value of R1 as 30 degrees. Now taking Snell's law at the interface SC, taking Snell's law at that, n sine I, so n sine I, which is 34.6, it was given in the question, is equal to the refractive index of this prism, which was also given as 1.51 sine this angle of refraction, which is 30 degrees. So that is nice law, and in this case we have only n as the only unknown, so you can make it the subject and it will be 1.3296. Therefore, we shall conclude that the refractive index of the liquid is 1.3296. It is okay if you use 2 decimal places. So that is how the 4 marks would be awarded. So now we shall go to part D. Part D says, explain how an optical cable transmits light. So here it is easier if we use a diagram. So let's first draw a diagram of an optical cable. Optical means that it transmits through signals through light, using light. So this is called the cladding or outer glass of lower refractive index. This one is called core, or which is the inner glass of higher refractive index. So this refractive index is higher than this, and this will be the beam of light. So that's why the word optical comes about. So you come and say that an optical cable is made of a transparent material called core coated with another transparent material called cladding of less optical density. So this one has a lower refractive index than this. That is why the density is also less. So you come and say that light entering the core strikes the boundary of the media at an angle of incidence greater than the critical angle, and thus total internal reflection occurs. So when the angle of incidence is greater than the critical angle, it implies that total internal reflection will occur. That is why here there is total internal reflection at all these points. So this takes place repeatedly in the core until the light beam emerges from the core, and in this way light is transmitted. So I think you can see there is total internal reflection until light emerges out of the core. So that is how an optical cable works, and that is how the marks would be awarded. So now we shall go to part E. Part E says, an optical pin held above a concave mirror containing water of refractive index 1.33 coincides with its image at a distance of 12 centimeters above the mirror. When the object is replaced by a little quantity of a certain liquid, the point of coincidence of the object and the image becomes 13.3 centimeters. Calculate the refractive index of the liquid. So know that refractive index is equal to real depth over apparent depth. Therefore, when the concave mirror contains water, this refractive index will be 1.33, real depth we don't know it, and apparent depth is 12. Therefore, when I cross multiply, real depth will be equal to 15.96 centimeters. When the concave mirror contains a certain liquid, still we shall use the same formula. Refractive index is equal to real depth over apparent depth. So the good thing, we know the real depth, so we shall come and substitute real depth and over the apparent depth which was given in the question, and the refractive index will now be equal to 1.2. So that is how the marks would be awarded. That was question 1. Now we shall go to question 2, part A, which says that what is meant by the term Roman 1 refraction and Roman 2 absolute refractive index. So refraction of light is a change in the speed or velocity of light as it travels from one medium to another medium of different optical density. Now this last condition, most students forget it, but this last condition is very vital in our definition. So always don't forget this condition, that the optical densities must be different. Then Roman 2, they want a definition for absolute refractive index. So shall come and say that absolute refractive index is the ratio of speed of light in vacuum to speed of light in a given medium, as simple as that. However, you can also define it as the constant ratio of sine of angle of incidence to sine of angle of refraction for a ray of light moving from vacuum to a given medium. So any of the two definitions is okay, and that is how marks would be awarded. So now we shall go to part B. Part B says describe an experiment to determine the refractive index of a liquid using a traveling microscope. So we need a diagram to help us is the description. So this is called a travel microscope. This is the container. That is the white sheet, and this is the test liquid. So that diagram can come and describe our experiment and say that a travel microscope is focused on a chalk particle put in a beaker and the reading A in centimeters is read and recorded from the vernier scale. So this is the vernier scale attached on the travel microscope. Then the chalk particle is this one here. So remember, this reading is read without this liquid, without any liquid. You just put a beaker, then put this chalk particle, then you can get the reading on the vernier scale and let it be A. Then the liquid whose refractive index is required is poured into the container and the travel microscope is raised until the particle is refocused. The reading B in centimeters is read and recorded from the vernier scale. So the new reading B, when there is a liquid whose refractive index is required, is also read. Then some chalk particles are then sprinkled on top of the liquid and the travel microscope is raised until the particles are refocused. The reading C in centimeters is read and recorded from the vernier scale. So before we go to the next slide, that's how the marks will be awarded for this slide. So now the refractive index n of the liquid can be obtained from the expression that n is equal to magnitude of C minus A over magnitude of C minus B. And basically that is what they wanted. So now we shall go to part C, Roman 1. So part C says that the figure below shows monochromatic light X incident towards A on a vertical screen. When the semicircular glass block is placed across the path with its flat face parallel to the screen, a bright spot is formed at A. When this flat surface is parallel like this, then a spot is formed at A. When the glass block is rotated about the horizontal axis through O, the bright spot moves down from A towards B, and then just disappears. Note this word, just disappears at B, a distance of 1.68 centimeters from A. Roman 1. Find the refractive index of the material of the glass block. I think let's start with Roman 1. So here we shall first redraw the diagram to complete the ray of light. Now, because they told us that the ray just disappears, note that word just. This word just is very vital. The word just means that the ray has glazed this surface. That is why here it is along that flat surface of the semicircle or semicircle. Okay. So when the spot just disappears at B, then total internal refraction has just occurred at O. It has just, and I think you note that word just. Therefore, from triangle AOB, it implies that tan is equal to opposite over adjacent. So opposite is here, and adjacent is AO. And AO, we already know that is equal to 1.5 centimeters. So tan theta will be equal to 1.68 over 1.5. Therefore, theta will be equal to 48.24 degrees. Then by geometry, we know that C is equal to C plus 148.2 plus 90 degrees equal to 180 degrees. That is because angles on a straight line add up to 180 degrees. So when I add all these angles, C plus 90 plus this theta which I've already got, I must get 180 degrees. Now when I make C the subjects, it will be equal to 76 degrees. So for this slide, those are the marks. And that's how the formats would be got for Roman 1. So now we shall go to part C, Roman 2. And C Roman 2 says, explain whether AB would be longer or shorter if a block of glass of higher refractive index was used. So you come and say that if the refractive index is higher, the ray is refracted more. Hence, AB would be longer. Then now shall go to part D, Roman 1. D Roman 1 says, a ray of monochromatic light is incident at a small angle of incidence on a small angled prism in air. Obtain the expression D is equal to n minus 1 in brackets multiplied by A for the deviation D. So D denotes the deviation of light by the prism. So you shall consider a ray of light passing through a small angled prism as shown. So that means that we need a diagram to ease the derivation. So that is a prism. So you shall have that ray incident on this prism. So if this prism was not there, the ray would have continued in a straight line, as you can see this dotted line. But because the prism is there, then it implies that it will be refracted along this path, and the angle of refraction would be R1. The deviation will now be D1. Then also for this one, at this point, it will also be refracted to this direction, and the deviation would be D2. So this I2 is what we call the angle of emergence, this is what we call the angle of incidence, and these are the angles of refraction. So that diagram, we can start our derivation. So taking Snell's law at M, we shall come up with sine I is equal to n sine R1. Remember, the refractive index of air is 1. That is why here you don't see any refractive index, because the refractive index would be 1. Then from there you shall come and remember that for small angle of incidence I1, expressed in radians, the angle of, so this is supposed to be of, the angle of refraction R1 is also small. So what does that mean? It implies that sine that angle approximates to that very angle. Therefore sine R1 also approximates to R1, and sine I1 approximates to I1. Now when I replace this with, remember this is sine I1, this is sine R1. So when I replace them with I1 and R1, I'll come up with I1 being equal to nR1. Then taking Snell's law at n, we shall come up with sine I2 is equal to n sine R2. So we shall come and say that for a small angled prism, A is small and hence R is also small. R2 is also small. This means that sine I2 approximates to I2, and also sine R2 approximates to R2, implying that I2 is equal to nR2. So that is how marks will be awarded for this slide. So the deviation produced by a small angled prism D is given by D1 plus D2. Now D1 is equal to I1 minus R1, and D2 is equal to I2 minus R2. When I rearrange, I'll come up with I1 plus I2 equal to minus R1 plus R2 in brackets. So I already know that I1 is equal to this and I2 is equal to that. So I can factorize out n to come up with this. And I already know that A is equal to R1 plus R2, therefore I can substitute to come up with this. Now A is common, so I can factorize out to come up with this, which is the required expression. So now we shall go to part D Roman 2. So D Roman 2 says calculate the minimum deviation produced by the 60-degree glass prism if the refractive index of glass is 1.50. So we know that refractive index is given by sine of D plus A over 2 over sine of A over 2, where D is the minimum deviation and A is the angle of the prism and N is the refractive index. So the angle of the prism was 60 degrees and the refractive index was 1.5, therefore D is the only unknown. Therefore I'll cross multiply. My aim is to make D the subject. So when I use the calculator, the whole of this gives me 0.75, because sine 30 is a half, and a half times 1.5 gives you 0.75. Therefore sine is equal to that. Then when I put arc sine, I'll come up with d plus 6 over 2 being equal to 48.59 degrees. Then next is to make d the subject, so I'll cross multiply, bring this to this side to come up with 97.18. Then next is to take this 6 at this side to come up with 37.18 as the value of d. So that is how the marks would be awarded. So now we shall go to question 3. Part A, Roman 1 says, state 2 conditions for total internal reflection to occur. So one is that light must be traveling from an optically denser medium to an optically less dense medium. Then the second condition is that the angle of incidence in the optically denser medium must be greater than the critical angle. So that is how marks would be awarded. So now we shall go to part A, Roman 2. A Roman 2 say that in the figure above, a parallel-sided glass slide is in contact with the liquid on one side and air on the other side. So here it is in contact with the liquid and here it is in contact with the air. A ray of light incident on the glass slide from the liquid emerges in air along the glass surface, as you can see it here. Derive an expression for the absolute refractive index NL of the liquid in terms of the absolute refractive index N of glass and the angle of incidence I. So we shall come and say that when the light is just cut off from the observer, it glazes the glass air boundary. So let's first redraw the diagram to ease the derivation. Okay, so now we shall come and say that taking Snell's law at the glass air interface. So at this point, taking Snell's law shall come up with N sine R, which is here for the glass, is equal to NA, which is the relative index of air, sine 90 degrees, which is this. But the relative index of air, we already know that it's equal to 1, therefore, and sine 90 is also equal to 1, therefore sine r will be equal to 1 over n, therefore r will be equal to arc sine 1 over n. Then taking Snell's law at the liquid glass interface, at this point, NL sine I is equal to n sine r. Therefore, when I come and substitute for r, I'll come up with this. Therefore, NL will be equal to n sine of arc sine 1 over n over sine I. Remember, they told us to express in terms of n and I. That is, otherwise, if not, they would have simplified this to come up with 1 over n, then multiplies by this. But we don't need to simplify because they told us express in terms of n and I. So that is how the marks would be awarded. So now we shall go to part B. And part B says, two parallel-sided blocks A and B of thickness 4.0 centimeters and 5.0 centimeters respectively are arranged such that A lies on the object O as shown in figure above. Calculate the apparent displacement of O when observed from directly above, if the refractive indices of A and B are this and this respectively. So this is for A and this is for B. So you already know the formula that displacement is equal to thickness in brackets 1 minus 1 over n. Now we shall do that for both A and for B. Then we shall substitute thickness of A was 4, then refractive index was 1.52. Thickness of B was 5, refractive index was 1.66. So when I use the calculator, I'll come up with 3.3564 centimeters. So now we shall go to part C, Roman 1. Part C says a tube of glass of sides 3 centimeters and refractive index 1.5 is placed in a thin film of a liquid as shown in figure below. This one. A ray of light in a vertical plane in figure above strikes side AB of the glass tube at an angle I which is equal to 41 degrees. So this angle is equal to 41 degrees. After refraction at X, the ray is reflected at the critical angle for the glass liquid interface. Roman 1. Calculate the critical angle for the glass liquid interface. So let's start with Roman 1. So first of all, we shall complete the ray diagram of how light travels. So this is our angle of incidence. So the angle, remember they gave us the angle to the surface, but the angle of incidence is measured between the ray and the normal. Therefore, I1 will be the angle of incidence. So at this point, it is refracted with an angle of refraction R1, but they told us that at this point, it is reflected with the critical angle. So that is why you see here 60 to mean the critical angle. So you come as that I1 is 41 degrees was given the question, therefore, sorry, I is 41, therefore I1 can be got because the whole of this is 90 degrees. Therefore, I1 will be 90 minus 41, which is 49 degrees. Then taking Snell's law at X, we shall come up with sine 49 equal to 1.5 sine R1. Make R1 the subject to be 30.21 degrees. Therefore, C, remember this angle is 90 degrees. Therefore, this plus this must add up to 90. Therefore, C will be equal to 90 minus 30.21. That gives you C as 59.79 degrees. And that was Roman 1. Then for Roman 2, they told us that find the position from B where the ray strikes the glass liquid interface. So the tan R1 is equal to opposite over adjacent. Therefore, the distance they want is this BY. So BY, we don't know it, but we know that from here to here is 1 centimeter. So shall come and substitute for BX and also for R1. Therefore, make BY the subject. BY will be equal to 1.717 centimeters. So that is how marks would be awarded. So shall come as that as the sun sets, the layers of air near the earth get cooler and therefore more denser than the layers of air higher up. This means that light from the sun is therefore continually refracted towards the normal. Therefore, rays from the sun which would propagate away from the earth are therefore refracted onto the earth. And since the eye sees images in the direction of the final rays reaching it, it therefore implies that when the final rays are received by the observer on the earth, they will give an impression that of the presence of the sun above the horizon. And that's how the marks would be awarded. So now shall go to question 4. Part A says, explain how mirages are formed. So first we shall need a red diagram to help us in the explanation. So we shall come and say that on a hot day, air near the tarmac road gets hotter, and hence the density of air reduces as the road is approached. That is why here the one which is far is cool and the one which is near the tarmac road is warm. A downward ray of light from the blue sky is thus refracted gradually away from the normal until at some layer of air where the critical angle is reached. So to be refracted away from the normal up at this point where critical angle is reached. So beyond this point, the ray is totally internally reflected. So at beyond that point, it is totally internally reflected. A distant observer E sees the image of the blue sky as if there is a pool of water on the road. So this pool of water is what we call mirage. And that is how marks would be awarded. So now shall go to part B, Roman 1. So part B says that monochromatic light is incident at an angle of 30 degrees on a glass prism of refractive index 1.50. The emergent light glazes, as you can see it here, it glazes the surface of the prism as shown. Roman 1, calculate the angle of refraction R. So they want this value. So taking Snell's law at the first refracting surface, we shall come up with sine 30 degrees is equal to 1.5 sine R. That means that R will be equal to 19.47 degrees. So that was Roman 1. What about Roman 2? Roman 2, find the critical angle C for the glass-air interface. So taking Snell's law at the second refracting surface, 1.5 sine C is equal to sine 90. Therefore, C will be equal to 41.81 degrees. So that was Roman 2. What about Roman 3? Roman 3 says find the refracting angle A of the glass of the prism. So A is be equal to R plus C, therefore R is that, C is that. When you add, you come up with 61.28 degrees. and that is how marks will be awarded. So now shall go to part C, Roman 1. So Roman 1 says, for array of light passing through a prism, what is the condition for minimum deviation to occur? So you come as that for minimum deviation to occur, the ray must be passing symmetrically through the prism and the angle of incidence must be equal to the angle of emergence. So that was Roman 1. What about Roman 2? Roman 2 says, describe how you would measure the minimum deviation d of a ray of light passing through a glass prism. So we need a diagram to help us in the description. So that is monochromatic source of light. Then shall need also a collimator, which is this. Then shall need the prism. That's the ray from the collimator. This will be the telescope with a prism present, though, so this is the position of the telescope with the prism absent. So marks for that slide, those are the marks for this slide, and this is the diagram to help us in the description. Remember, before you carry out any description, you have to first make the initial adjustments. One is that first the telescope is adjusted so that power rays entering it are brought into sharp focus at the cross wires. That was the telescope. What about the collimator? The collimator is adjusted to produce parallel rays. What about the circular table? The circular table is leveled. So those are the initial adjustments. So now we can go to the description. So shall come as that the prism is now placed on the table with its refracting edge facing away from the collimator. The telescope is then turned to receive the refracted light from the opposite face of the prism. The table is rotated while keeping the image of the slit at the center of the cross wires until a point is reached when the slit image begins to move in the opposite direction to that in which it has been moving. The position T1 of the telescope on the circular scale is noted. So that's how marks will be awarded for this slide. Now let's go to the next slide. The prism is now removed and the telescope turned to receive light directly from the collimator. The new position T2 of the telescope is again noted. The angle between the two positions T1 and T2 is determined, and it's the angle of minimum deviation D. So that is how minimum deviation could be got. So now shall go to part C, Roman 3. C Roman 3 says, if the angle of minimum deviation in C Roman 2 above is 41 degrees, for a glass prism of refracting angle of 60 degrees, find the refractive index of glass. So that's the formula for refractive index. Then you substitute D, A, and A. In the end, you come up with 1.54. and that is how marks would be awarded. So now shall go to question 5. Part A, Roman 1 says, explain total internal reflection and give 2 instances where it is applied. So you have that for small angles of incidence I, a ray of light traveling from a more dense medium to a less dense medium is partly reflected and partly refracted as shown below. So let's draw a diagram. So there are 2 mediums. There's the incident ray. That ray will be partly refracted and also partly reflected. After that, we shall come as that increasing the angle of incidence I increases the angle of refraction R simultaneously. So as this angle is increased, this one is also increased. And that's how marks will be awarded for this slide. When the angle of refraction in the adjoining less dense medium is 90 degrees, the angle of incidence in the denser medium is known as the critical angle for the given mediums. And when the angle of incidence in the denser medium exceeds the critical angle, no refraction occurs, and the entire incident light is reflected back into the dense medium. This phenomenon is what we call total internal reflection. So now shall go to part A, Roman 2. Roman 2 says, give 2 reasons for using prisms rather than plane mirrors in reflecting optical instruments. So one shows that there is no loss of energy in total internal reflection in prisms, while in plane mirrors there is some loss of energy on refraction at plane mirror. Then 2 shows that no silvering is needed on prisms, while on plane mirrors silvering is needed and it wears off with time. Then 3 shows that there is no multiple images in prisms, while in plane mirrors multiple images are formed. So basically that's how the marks will be awarded. And now shall go to part B. Part B says derive an expression for the apparent displacement of an object when viewed normally through a parallel-sided glass block. So you consider a point object O at the bottom of a glass block being viewed normally by an observer from above. So that is the point object, and this is the observer, and this is the glass block with thickness T. Now rays OA and OB from O are refracted away from the normal and appear to come from point I to the observer as shown. So you have a ray OA which is refracted away from the normal, and it appears to come from this point. Also, ray OB is refracted away from the normal and appears to come from this point, which is point I. So taking Snell's law at B, we shall come up with n sine I equal to na sine r. But from right angled triangle, sine I will be equal to nb over OB, because sine is opposite over hypotenuse. And also sine r will be nb over ib, which is opposite is nb and hypotenuse is ib. The refractive index of air is known as 1. And those are the marks for this slide. So when we substitute for sine I and sine r and for na, we shall come up with that. So this and this can cancel, you remain with n being equal to that. Now taking b to be close to n, it implies that OB approximates to ON and also IB approximates to IN. That implies that n is equal to ON. Where there is OB, we shall put the ON, and where there is IB, we shall put the IN. But remember, ON is T and IN is T minus D. Therefore, cross multiply and look for a way of making D the subject. So when I make D the subject, I'll come up with this, because here T is common, I can pull it out to remain with 1 minus 1 over N, which is the required expression. So that is how marks would be awarded. So now shall go to part C Roman 1. C Roman 1 says a glass block of refractive index Ng is immersed in a liquid of refractive index Nl. A ray of light is partially reflected and refracted at the interface such that the angle between the reflected ray and the refracted ray is 90 degrees. Show that Ng is equal to Nl tan alpha, where alpha is the angle of incidence from the liquid to glass. So that means that we need a diagram to ease the derivation. So we have the water and the glass, therefore that is angle alpha of the incident ray, refracted ray is that, partial refracted ray is that, and partial refracted ray is that. So because this is 90 and this is alpha, it implies that this remaining one will be 90 minus alpha. Therefore, taking Snell's law at the water glass interface, we shall come up with NL sine alpha is equal to NG sine 90 minus alpha. But we know that sine 90 minus alpha is the same as cos alpha. Therefore, bring this cos this side, sine over cos gives you tan, which is here. And that is what they wanted. So now we shall go to part C Roman 2. So C Roman 2 says that when the procedure in Roman 1 is repeated with the liquid removed and the angle of incidence increased by 8 degrees, given that NL is equal to 1.33, find NG and the angle of incidence at the liquid glass interface. So you already know that this is what you have got from here, so therefore that means that NL is here, implying that tan alpha is equal to Ng over 1.33. Therefore, when the liquid is removed, it implies that the angle increases by 8. That is why you see here, where there was alpha, we have put there alpha plus 8. And this, and where there is this, we have put there the refractive index of water, because of air, because now there is no liquid. Expanding this from trigonometry gives you that. cross multiply to come up with that. So simplify. So my aim is to remember here we got that tan alpha is equal to ng over 1.33, so we have come and substitute it here. Then also substitute here, which is that, to remain with that. So when I simplify using a calculator, I'll come up with that. So that is a quadratic in terms of ng, so I can use bulldozer method to come up with two values of ng, which is 1.39 and 0.95. But we have to eliminate one, so we shall come and say that for total internal reflection occurs when an array moves from a less dense to a more dense medium. Less meaning that ng cannot be equal to this because refractive index of air was 1, meaning that for this one to be more dense it must be greater than 1. That is why we take 1.39. Then from this, now we have got the value of ng. So from this it implies that where there is ng, put there that to come up with the value of alpha as 46.26. So that is how marks would be awarded. So that brings us to the end of this video. Thank you for watching, and next video will be on physics paper 1 test 5. So if you haven't yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp so that we can all benefit as a family.